Welcome back to the deep dive. Today we've got a stack of engineering postmortems, a bunch of research papers, all asking one really expensive question.
Why do machine learning models fail?
Exactly. And we're not talking about code that just crashes. We're looking at models that seem flawless in the lab.
They get great scores, everyone's happy.
And then they just completely collapse the moment they hit the real world.
It's a massive issue.
Yeah.
And what's so fascinating across all these sources is that the failure point is, well, it's almost never the complex math.
Right. It's not the algorithm itself. It's not that the brain isn't big enough or something.
Not at all. The papers call them foundational failures.
It's the plumbing. I see this theme where beginners, they treat the ML libraries like these magic boxes.
Yeah, you just pour data in one side.
And intelligence is supposed to come out the other. But the reality is that it's this really rigorous engineering discipline.
And if you don't treat it that way, you get these failures. It all starts with data hygiene.
Okay, so let's start there. Feature scaling. It sounds so minor, almost like a formatting thing.
It does, but its mathematical impact can be, well, catastrophic.
I loved the example in the notes. You have a data set, and it has age, let's say 30.
And then it has income, say, $100,000.
To a person, those are just different scales, different units. But the model doesn't get that, does it?
No, it's totally blind to context. It just sees the raw numbers. And since 100,000 is just so much bigger than 30,
it thinks income is way more important.
Way more important. It basically ignores age because the other number is just louder, mathematically speaking.
So you should normalize it first, squash everything into, a standard 0 to 1 range?
Otherwise, you've baked in a bias before you've even started training.
But even with perfect scaling, you hit what the literature calls the most insidious error.
Data leakage. This one's brutal.
Why brutal?
Because your model looks incredible during testing. You get these amazing scores and then nothing. Mm-hmm. It fails in production.
Because it cheated.
It cheated. It saw the answers.
Yeah. The lone default scenario was the real aha moment for me. You're building a model to predict if someone will default.
But you accidentally leave a column in the data, something like post-default collection status.
So the model just learns that if the status is sent to collections, the person defaulted.
A perfect one-to-one correlation. It's not learning the complex patterns before the default. It's just learning the outcome. That's future knowledge.
And that future knowledge doesn't exist for a new applicant, so the model is useless.
Totally useless. And that's tied to this idea of contamination, right?
Yes. That's cleaning the data before you split it into training and testing sets.
The classic mistake. If you, say, fill in missing values using the average of the entire data set,
then your training set has now seen information from your test set. You've leaked data across the barrier.
You have to split first, then clean.
Always. Okay, so the data is clean, no leakage. We still need to know if the model is actually any good. And this is where we hit the accuracy paradox.
This is so critical. Everyone is trained to think accuracy is the goal.
The North Star metric.
But imagine you're detecting credit card fraud. Real fraud is, maybe 0.1% of all transactions?
A tiny fraction.
So I could build a model that just predicts no fraud every single time.
And you'd be 99.9% accurate.
And 100% useless. You didn't catch a single crime.
So for these imbalanced cases like fraud or rare disease screening,
how many of the actual positive cases did you manage to find?
You'd want high recall for cancer screening. You'd rather have a few false alarms than miss a real case.
Exactly. But there's a human bias here too, isn't there? The sources call it complexity bias.
Oh, definitely. Everyone wants to jump straight to the huge, deep neural network.
It's the shiny new toy. But the advice here is so simple. Start with a baseline. A simple logistic regression.
And if your giant complex model doesn't crush that simple baseline,
then you probably don't need it. The complexity just adds debt and makes it a nightmare to debug.
Speaking of debugging, let's touch on categorical encoding. This is such a classic pitfall.
It is. You have categories like cities, New York, LA, Chicago. You have to turn them into numbers for the model.
So you make them 1, 2, and 3.
And the model immediately thinks there's an order. It thinks Chicago, being 3, is somehow mathematically greater than New York at 1.
Which is just meaningless.
It's trying to find a trend that doesn't exist. You have to use something like one-hot encoding to stop it from hallucinating a hierarchy.
It really does feel like the whole journey from novice to expert is moving from focusing on the algorithm itself,
from algorithmic novelty,
to focusing on systematic rigor, the whole system around the model.
That's the key takeaway. The code is the easy part. The discipline is everything else.
And on that note, here's a final thought for you to chew on. The sources talk a lot about proxies.
The hidden correlations.
Yeah, you think, okay, I don't want my model to use this sensitive variable, so I'll just delete the column.
But the model is an optimization machine. It will find a shortcut. If you leave in something like, say, zip code,
It can use that as a proxy to basically reconstruct the information you tried to hide.
exactly, it finds the pattern you told it to ignore.
Which leaves us with a really tough question for your next build.
Yeah.
How do you audit a black box for biases you can't even see? Something to consider. Thanks for deep diving with us.